Sorry. Yeah, I just want to make sure because these people are always missing on this day, so I want to make sure they get what they need. We worked it out before classes began this semester, so don't worry. It's not anything untoward going on. But anyway, so we have number 25 from the homework, just to make sure that we know how to do this, because the quiz is going to be sort of similar to this. So the first thing to do is to say that the error, if you add up the first in terms, oh, in is there, the first k terms, the error from when adding up the first, let's do k terms, the error is going to be the next term. So if we stop at 10, the error is term number 11. If we stop at 20, the next one is the error. So we'll do this, the error here. So the error, I wrote that twice for some reason, is going to be 1 over k plus 1 squared times 2 to the k plus 1. And I want that to be less than 5 over 10,000. So you know how I'm going to do this is I'm going to just cross multiply because these are all positive numbers. So I want 10,000 to be less than 5 times k plus 1 squared times 2 to the k plus 1. So that means that, I guess, divide by 5, 2,000 is less than k plus 1 squared times 2 to the k plus 1. I suspect that the thing that's going to be the bully here is the 2 to the k plus 1. And if you're at all familiar with powers of 2, you know that 2 to the 10th is 1,024, 2 to the 9th is 512. So the computer nerds here probably are familiar with those numbers, as well as some other powers of 2. 256 is 2 to the 8th. So since I want to get to 2,000, and you got to remember this thing's here, I'm guessing that it's going to be around 7 or 8, because yeah, 2 to the 7th, even that is pretty big. So I'm just going to guess and check at this point. So starting with 2 to the 7th, which would be k equals 6, I think this is going to be too big right off the bat, but I'm going to do it anyway. So 7 squared is about 50 times 2 to the 7th is 6,272. So that's with k equals 6. Then if we set k equals 5, actually I think I might have hit it perfectly, because k equals 5 is 6 to the 2nd times 2 to the 6th, and that's 2,300. Okay, so I might want to jot this down. When k equals 5, you have 2,304, which is greater than 2,000. So k equals 4. So k equals 5, I think, is going to be the magic number. But let's just do k equals 4 for fun. So this is going to be 5 to the 2nd times 2 to the 5th. We know what 2 to the 5th is. Whoops. Oh no, my calculator just, it looks like the Matrix, like, I don't know what happened there. Let me quit. I think it's dead. Well, I killed it. Here, I'll do it in my head. K equals 4, 5 squared, 25, 32. 25 times 32 is 800. All right, sure. We're going to go with it. 800, which is less than 2,000. And so k equals 5 is the magic number. That's what we're looking for. Let's see if this one will work on my Python. Let's see if this will work. I don't know if it will. Just a second. I need to be able to see this on both sides here. Okay, so let's see. I need the formula. It's going to be -1 to the n minus 1. So -1 to the n minus 1 times, oh yeah, I did this, by the way, yeah, ignore that. I did this morning with the 4 over, you remember the odd numbers, 4 over 1 minus 4 over 3 plus 4 over 5. I wanted to see how far I would need to go. Well, we could figure this out, but I just wanted to demonstrate it. And so I did this by adding up all of these. So these are partial sums, and this is the 94 millionth, 94.3 millionth partial sum, and then 94.4 millionth, and so on. And it finally got to within, how many digits was I looking for? Sorry, oh, now I'm on this, I'm at the bottom. How can I get back up? Okay, well, it finally got to, let's see, however many digits this is. That's what I was looking for, is 7 digits. It finally got there, almost 10 million. It was like, or almost 100 million. It was like 99 million was how many times it had to do it. So that's what that code is. It was just adding up, sort of doing partial sums and saying, how close am I? Okay, so this is just using SymPy. You can do sums. You can do calculus. It's the same as using, what is it called? Your Desmos or whatever it is. So this is going to be n squared. Sorry, it's just going to take me a minute to do this. N, squared times 2 to the n, let's see, 2 to the n. Okay, there it is. I think that's it. N squared times 2 to the n. Okay, that does it. Okay, let's see what this gets. Oh, infinity. Yeah, well, there's n squared here, n squared. Maybe I need to put enough parentheses here so that it understands. All of this stuff is in the denominator. Shouldn't this not be infinity? It shouldn't be infinity. Maybe it just can't do this one. Oh, I got so excited that it got pi with that other one. Do I have this typed right? It's -1 to the n minus 1 times 1 over n squared times 2 to the n. And we're integrating, we're integrating from 1. Aha, I see. Yeah, if you start at 0, you get 1 over 0. Okay, it was fine. No. Apparently it doesn't know. Well, it does. That's a number, but it's not a number that I like to think about. So I'm going to switch. So, but anyway, let's go back to this so that we can do more if we need to. But you understand that the error is the next term. And we can actually, does it say we should add these up? So we can add these up. Let's do it. So we have 1 over 2 minus 1 over, what's 4 times 4 is 16, plus 1 over, I'm just plugging in different numbers for n. So this is going to be n equals 3. N equals 3, I get 9 times 8, 72, minus 1 over 4 squared is 16. 16 times 2 to the 4th. That shouldn't be too hard. 16 times 16 is 256. And then plus, so we're just going to do 5 of these terms. So 1 over 5. Oh, we did this already, right? It's 800. Okay, so if we did that on a calculator, but my calculator is broken now, we would get the, we would be within that error. So we would, you just add up that many and you'd be all set. So on the quiz, I just tell you add up 3. So if you were doing my quiz with this, I say add up the first 3 terms, which would be just to here. You can do that. And then tell me how close you are to the truth. You would tell me this. So it's always the next term. So that's how close we are to the truth if we add up the first 3 and so on. And then I ask you some other question, but hopefully that'll do it. Any other questions about the quiz? Yeah, or about the homework? What do you think, Hayden? Oh, okay. So this, the error is always the next term. So let's just take a look at 23 just to see. So if we were going to add up, so let's just say we added up with this one, we did 1 over 1 minus 1 over 64 plus 1 over 3 to the 6th, just a minute, 729. Is that 3 to the 6th? 729, we're going to pretend. Yeah? Okay, good. Okay, so let's just say that we stopped after 3 terms. Then the error is going to be the next term, which is going to be what you get when you plug n plus 1, n equals 3 here. So n plus 1, so if n equals 3, then n plus 1 equals 4. So the error would be 1 over 4 to the 6th, and 4 to the 6th is 4,096? Right, wait, let me think about this for a minute. 4 to the 6th is the same as 2 to the 12th. Yeah, 4,096. So anyway, that's the error involved. It's always the next term. So all I was doing here is I was saying if we add up the first k terms, I'm just going to put k plus 1 in here. Now, if it bothers you, the k plus 1, you could always just plug k into this, but then bear in mind that you're getting the error, and so you would have to subtract 1 from whatever you got. So if the k plus 1 bothers you, you could do it this way. Here, I'll just show you really quick. 1 over k squared times 2 to the k has to be less than 0.00005 or whatever, how many zeros? I have an extra 0. So you could do it this way and then solve for k, but then bear in mind that k would be 1 more than the terms that you needed.
So basically take the value of n, substitute for k at 1, because we're looking for n plus 1 of that.
Yeah, well, the reason I'm not using in is because in is already being used here, so I'm just using another letter. You could use in, and I will not fault you. If you put an in here, I'm not going to complain because I know what you mean, but it's technically not correct. So, and being a mathematician, I'm under contract to do it the right way, but I'm happy to be lenient when I see your quiz, especially yours, Hayden. Anyone else have any questions about this? You think you can do it? Hopefully, maybe. Let's give it a go. All right, so let's give this a go. I got one here for you. I'll put it up on the screen for the people watching from home in a minute. You can fast forward if you get bored. Here's 3 up here. Here's 2 right there. Enjoy. Here's 3, I think, maybe more. I don't know. We'll find out. There you go. Enjoy. There. 2, 3. You got a few. That's probably too many. There. I know you're last. I got to come back here first next time. I'll try to. I know, but every now and then I remember. So that's the thing, is if I tell it to myself enough, I'll figure it out. I'll remember. You've got an extra one? Good. Anyone have extra one? There should be one extra one. Oh, no extras. Well, good thing I. Oh, that's the next term.
Oh, okay.
Yeah, that's what I mean. Is what's the error? What's the bound? Just how big can the error be? Yeah. Okay, let me find this quiz here somewhere. Here we go. Calculus. Where's this thing? Seven. Well, I'm hoping that you're coming down the home stretch with this. If you're still working on it, maybe you can try to wrap things up. I'm just doing a couple things, then I'll come get what you have. All right. Well, if you are done, feel free to send it over. If you aren't, don't panic just yet. It's gonna be okay. Thank you. Thank you very much. Very nice. Thanks, sir. That's interesting. Yes. This looks okay? All right. You all set, Caleb? You have a little pile for me. Very nice. Good job. Good job. All right, so those of you who are still working on it, try to finish up. Maybe you're doing some guessing and checking. Not a whole lot to guess and check, though. It shouldn't be too big of a number that you have to deal with. All right, so I'm going to come around and see what you have. Probably just want to put a box around that number. Very nice. Yeah, you don't have to write a sentence. I mean, you might as well put a period at the end, though, since you already have. Nice. You're doing a great job. Good job. Yeah. Yeah. Just curious. I'm just curious what's happening here. Okay. Very nice. Thank you. What's that? You have two of them? Oh, you are the extra one. I was wondering where it was. Okay, thank you. All right, you can do it. You can do it. Yeah, I like it. I like it. It's looking good. Yeah, keep going. Keep going. Doing great. Oh, yeah, you're all done. Very nice. Beautiful. Just getting that last bit. Oh, yeah, you're obsessing over this, I think. No, this is perfect. Yeah, this is, I love this. Not making you nervous, am I? I'm just peeking over your shoulder, looking to see what you've done. Very nice. Beautiful. Interesting. I like it. You got it in the fraction form there. So is this your number that you like? Oh, yeah. Pick one. Pick one. Wait, that one's in. This one's K. You should go with it. Go with N. Yeah, go with the N. Yeah. Do it. Box it up here. It's beautiful. Nice. Did you get it? Oh, you did get it. And you've got it. You're all set. Nice work. Beautiful. Oh, I love it. Anyone else? You need yours back? No? Looked like you were waiting. All right, did I get them all? Okay, the staple's going in. Ooh, one more. Almost got left out of the fun. All right, very nice. Okay. Oh, I have stuff to give back. Oh, well. We'll get it back, don't worry. Okay, so let's take a look at what I did. Hopefully I got it right. So there's the first one. So you're just adding the first three terms. So that's -1 to the first over 2 to the first plus 1, that's that. And then -1 to the first or the second, and then 2 to the second, and then that. So I got that. And then the error is it's always going to be less than the next term. And the next term is what you get when you plug 4 into this, well, without the negative stuff. So it's 3 over 2 to the fourth plus 1. So there's the error. So something like that. I saw a couple of you actually put, is this 11/15ths or something? So well done. I just did it as a decimal. I was too lazy to figure out the common denominator. And then down here, you're just looking for where the term exceeds, well, actually, when the term is less than this, because the next term is the error. And so just a little bit of algebra here. 2 to the n plus 1 has to be bigger than 3,000. So I just moved the 1 over to the other side. And then I got this because I thought it would be fun to do it that way. But you could just guess and check at that point, like right here. That's fine. Yeah, I did it with my calculator. And so n plus 1 had to be bigger than 11.55, which means if you have n equals 11, 11 plus 1 is 12, which is bigger than 11.55. So that does it. So well done if you got that. If you didn't, maybe you're off by 1. It's fine. Okay, so what are we doing today? Today we're kind of wrapping up the series stuff because the next section, well, actually the next section, we're not quite to getting functions, but the goal of all of this, I think I've mentioned this, the goal of all of this is to take a function like this, e to the x, and express it as a series. So n equals 0 to infinity. So this is a little preview, I guess, of x to the n over n factorial. This is going to be one of your favorites. So this is a series representation for e to the x. And this is how I know when I look at, you remember there were some series that we did yesterday, and I said, oh, yeah, that one converges to this number. And the reason I knew that was because I knew that this was the function that the functional representation of this. There are a couple of others that you're going to become familiar with. For example, 1 over 1 minus x is this sum, n equals 0 to infinity of x to the n. So interestingly, that function. This is only true when x is between 1 and -1. I should put this in, not in parentheses. Yeah. So this is when, yeah. Otherwise, it's not true. So this one up here is always true. Always true. So this is our goal. Our goal is to get to this point where we can understand, when does a function equal a series? Because if you can write a function like a series, like this, instead of that, then you can actually do calculus with it or solve problems because you're used to solving problems with polynomials. You all know polynomials are way easier than, say, the arctangent or natural log or whatever it is. So if we can take a function like this, or the natural log, do I remember this one? It's going to be the sum of -1 times x to the n over 2n plus, hold on a minute. No, that's not right. There's something wrong. This one, that's not natural log, that's arctan. But whatever. I've got my favorites. I've got a list of them, of these functions. That once you have a series, then you can treat your function the way you would treat polynomials. You're used to polynomials, so it's a lot easier. So what we're going to do today is we're actually going to sort of start the homework. So the homework, because I don't want to get started on the next section, which starts dealing with some of this more complicated stuff with series. So I thought we'll go back and we'll just do a little bit of review. So your homework for tomorrow, you have two things to do. You have the homework that's in the book, which is in the review exercises. So these are found at the end of the chapter. Chapter 11, end of the chapter, you'll find review exercises, and you'll see things like this. Anyway, let me make sure that we don't do the ones that you're going to be doing. but we're just going to pick a few of these. Give me a sec. And we will do them. Is this it here? Yeah, there it is. Okay, so your homework, just so you know, I don't have my glasses on a tether today, so this is harder. Okay, so your job, 11. So it's 11, 12. I'm just going to circle these so we can avoid them. 13, 15, 21. Hold on, 15, 21. Couple more. 23, 24. And 27, 28. So those are your homework. You'll find it online. It's online. Okay, but I wanted to get us to review some of this and just show you sort of the thought process. Now we're going to be using this. Where is it? Now I've lost I should relabel this. I think here it is. Is this it? Hold on a minute. Oh yeah, here it is. Here's my flow chart. So we're going to use this series flow chart in each case. So let's just review this really quick, and then we're going to go and try using this with some unknown series. You know what this feels like to me? It feels like when I was in organic chemistry, and they would say, okay, this is such and such a compound, this is such, and then you had a mystery compound, and you were supposed to figure out like what are the properties or whatever. And it was such a pain, and you'd go through a bunch of tests to try to figure out what was involved in this mystery organic compound. But anyway, so we're going to do the same thing here. We have a mystery series, and we're going to go through a bunch of tests. Of course, the first tests, just to remind you, are the geometric and P series. These are so important that we're going to just review them really quick. Let me get rid of all of my notes over on the right. We're going to make new notes. In just a sec, let's get rid of all of this mess. Delete, delete, gone. Okay, so just to remind you, if you have a series like this, 3 over 2 to the n, or this, you can tell whether it converges. Let me just put down 2 more because we need to review both of these. Okay, so then we have this sort of a thing. And this sort of a thing. Oh, I've got an F5. That's all right. So let's go through these one at a time. These are all quickies, and they are all going to fit into one of these 2 categories, geometric and P-series. So you should be familiar with these. You should be able to pull them right out of your brain, hopefully. But we'll come back here if we need to review. So tell me if this is a geometric or a P-series, and then tell me, does it converge or does it diverge? Where is my, this will give me a chance. Oh, here, I'll zoom out. You figure it out for these 4. There they are. And then that'll give me a chance to fix my attendance. Where did I put my attendance? Hold on a minute. It's here somewhere. It's not there. There it is. Okay. There you go. Good job. Okay. All right, let's randomize here. Michael H. Michael H. What do you think of this top one? Is that geometric or is it P-series? It is geometric. Very nice. So we have a geometric series here, geometric. And since it's geometric, there must be an R value for this one. Let me find someone. I know you all know this. Hunter, what's the R for this first geometric series? It's, did you say it's over 2? Okay, so this one's actually just 1 over 2. And the reason is that 3, you'll notice the difference here. The 3 does not have an exponent. It's just 3. So that is actually the same. And I noticed on the quiz that I need to hand back to you that some of you made this mistake, is you lumped the 3 in with the 2. This is the same as this. Because the 3 doesn't have an exponent, you can write this like that. And so the r is actually just 1/2. So here, I'll get rid of this and write it like this. There we go. So bear in mind that if there's no exponent or no n, then that is just constant and can be pulled outside the summation, and then that's what we're dealing with. Well done. So now we have to figure out, does this converge or does it diverge? Maggie knows, don't you, Maggie? This one converges. I'll put a big C here for converge because the r, Maggie knows this, that when the r is between -1 and 1, you're converging. When the r is either bigger than 1 or less than -1, you diverge. Very nice. Okay, let's do this next one. Next one, I think you can figure out that that one is also geometric. But Eli, what is r for this geometric series? Now this one is 3/2. So yeah, I snuck it in there. I thought, well, let's make sure that we know the difference between these. So here the 3 is not part of the geometric thing, but here it is because it is raised to that exponent. Very nice. And so then finally we have to figure out, does this converge or diverge? Ben P, you know, does this converge or diverge? Yeah, it diverges because r is bigger than 1. So this one's a big D for diverge. Very nice. Okay, now I think you can probably guess that I've got 2 P series down here. So both of these are P series. P series. So let's just review this. And you gotta know these. I mean, you should be able to, these, if anyone gets any of these wrong, the basics, I don't know how you can even continue because, well, I mean, on the test. You can get them wrong today. It's totally appropriate, in fact, because that's why I do this, is to give you lots of chances to fail before the test, because if you fail now, it's like, it doesn't even matter today because we're not even collecting this. So feel free to get it wrong now. But on the test, if you don't know these, how are you going to be able to do the comparison tests? Because that's the next thing. So anyway, let's do these. Let's see, who are we doing it with? Andrew. Andrew, what about that first one? If these are both P series, what's the P for this first one? Oh, very nice, 1/2. And of course, the reason Andrew knew this is because he knows that P means power, power. So n equals 1 to infinity of 1 over n to the 1/2 power. So there's the power, P is 1/2. Now we just need to know if that diverges or converges. Christian, can you help us out? Does that converge or diverge? Very nice, because Christian has this one memorized, and it's that the P series, so this is like the opposite of the geometric series. The P series will converge only when the P is a big number, and if P is less than or equal to 1, you diverge. So very nice. So then this last one is pretty straightforward since we've got this. Hayden, do you know about this last one? Do you know this one? Does it converge or diverge? Nice. There you go. P is 5, so this thing converges. Very good. Okay, so we've got that. So I wanted to I'm not going to review the rest of these other than just to give lip service to them, but these are so essential because we use them when we're doing the comparison tests. So you got to know those. Okay, so let's just make sure we remember these other ones. This next one feels similar to what we just did when we did the alternating series test. And all this says is that if you have a sequence that doesn't go to 0, then the series diverges. So we might have some examples of this in just a bit, but for now, we'll just remember that and we'll use it. The next one is if you have a positive decreasing sequence, then you could use the integral test. And I have a question mark here only because the integral test requires you to compute an integral. And if it's a difficult integral, then maybe not, you know? Oh, for example, here, I'll show you a difficult integral. If you have this sum, n goes from 0 to infinity of e to the negative n squared. If you have that as your sum, you might say, oh, can I, that's a decreasing positive sequence of numbers. But that would require us to do this integral, e to the negative x squared, which you might know is a finite number, but there is no elementary function antiderivative for that. You can punch it into Desmos and it'll be like, I don't know. But it's not, it's finite. So that's why I say question mark, is that maybe you'll want to use the integral test. Maybe not. Like with this, I would probably use a comparison test or something else. Yeah, technically that's going to be less than a geometric series. So we could go with a comparison test then. But anyway, getting back here, can we compare? If you can think of something to compare with, then you might as well do a comparison test. So, but once again, only if there's other stuff. So that's the thing about this, is you do the easy stuff. If there's something easy that you can do, you do that. And then if you can't, move on to the next one. So direct, we'll do some comparing here. Oh, let's do comparison for this one, e to the negative n squared. So give me a sec. N equals 0 to infinity of e to the negative n squared. This is actually a simple direct comparison. Can anyone, I won't pick anyone out of the blue, but can anyone think of what you might compare this to that's a relatively easy thing? Yeah, oh, what do you got, Ben? Yeah, 1 over e to the n. And the reason why this works is because this is 1 over e to the n squared. Here, maybe I should write it like that. Just a minute. So this one is 1 over e to the n squared, and that's going to be less than this 1 over e to the n. Because you know the drill is if you have a smaller denominator, which e to the n squared, as long as n is bigger than 0, as long as n is bigger than 1, e to the n squared is way bigger than e to the n. And so that will be a bigger denominator, which means it's a smaller sum. And so this one is geometric, and that converges because 1 over e to the n. Yeah, oh, maybe this is confusing. I'm beginning to see. Okay, here, let's jot this down real quick. 3 over 2 to the n is not equal to 3 over 2 to the n. But 1 over 2 to the n is equal to 1 over 2 to the n. And the reason for that is because 1 to the n is equal to 1. There. So that's the string. So 3 to the n is not equal to 3. So you can't do this, but this you can do. So maybe that's why everyone was like, oh yeah, let's just throw the 3 in there. It doesn't belong, don't do it. Okay, but anyway, this is less than, this one converges because 1 over e is less than 1, and so that converges. That's a direct comparison. So if you can compare, and this is, I should say, only do this if it's easy. Is there, here, just a minute, put this up top. Is there an easy comparison? Can you easily compare? That looks wrong. Just a minute. Easily. There. So, can you easily compare? Yes, we'll do it. If you can't easily compare, then let's go find something else to do. And so then you have this alternating series. That's the one we just did. So I didn't put the, but you know the drill for alternating series. So what's going to happen is after we take our test, we're going to add to this. There are 2 more tests so that you know what they are. I'll tell you what they are right now. There is the ratio test. These are kind of in the same category. So I'll put them in the same. So ratio or root test. It's kind of the test of last resort. These 2 tests, like if you can't do anything easy, you might as well do this because this isn't terrible, but it's not super easy. So we'll do that next week. So that's later, and that's pretty much it. If you, yeah, so here we go. This is yes, and if it's a no, then you give up. Yeah, so this is like the last resort down here. What do you think, Hayden?
So it's like the ratio of root covering the formula, like formula.
Yeah, you're right. Yeah, so yeah, if you can't factor, you might as well use quadratic formula. It's a little bit more painful, but it always works. Even if you could have factored, sometimes I remember this, I would be trying to factor, I can't do it, so I use the quadratic formula, and then it's like, oh, I could have factored, now I see it. So yeah, that sort of thing sometimes happens, but yeah, it's like a catch-all. Generally, it will work. The ratio and root tests, generally they will work one way. They'll tell you if you converge or diverge. But we're going to restrict ourselves to the stuff above this right now. Let's go back to the review section and take a look at a few of these. And so I've circled the ones that you're going to do on your homework. So let's do some of the other ones. This one looks fun. This one, why not? Yeah, some of these I'm looking at and I realize they're going to end up using the ratio or root test, but we might as well see what happens in those. Okay, yeah, let's do a few of these. So let's start with this one here. So notice what these are. They're just sort of generic. Determine whether the series converges or diverges. So we'll just go through, 11 you're going to do. Okay, so we'll just go through and do some of the ones that you aren't going to do for me, just to get a feel for this. So number 14, as we go through the list, so I'm going to do this one, and this is going to be painful because I think most of you know what the answer is, how we're going to do this, but allow me. So as I go through the list, I think to myself, is this geometric? No. Is it a P-series? No. I mean, it sort of looks P-series-like, but it's not. Okay, so it's not a geometric, it's not a P-series. Can I do a direct comparison? Well, the problem with the comparison tests are that they require positive sequences. This is not positive, you have a negative here. So once you see the negative, you're going to be stuck skipping all of the easy things and going down to the alternating series, which is not too bad. So maybe I should go back here and just point that out. Hold on a minute. So here. Let's see. So back here, yeah, this, you know what? I guess I should have had, my flow chart should have been a little different. So can you compare? And so maybe I should put here, this is for positive, only positive. So you have to be positive to be able to compare. So if you have a decreasing positive sequence, then you can use the integral test. But if you're positive, even if you're not decreasing, and you might say, well, if it's not decreasing, isn't it divergent? No. There's examples. I can show you one. Not now. I don't want to bore you with it. But anyway, so can you compare easily? Then you do that. And then so basically, if you have something that's negative, if it's negative, then you're stuck doing this. So maybe I should even say here, have a little branch, negative. Then you skip all of this stuff and you go down there. So yeah, if it's not a P-series, if it's not geometric, then we go to the bottom. Oh, I should do this though. Is the limit equal to 0? Let's check that. Wait, what did I just do? What am I doing? Here's what I do. Okay, yeah, let's go check that. So that's an easy thing to check. Is the limit equal to 0? You can sort of just do it in your head. Well, the limit as n approaches infinity of this, that doesn't count because that's always positive or negative 1. This gets bigger and bigger. So as n goes to infinity, this thing does go to 0. So I can't conclude that that diverges, sadly. So we're down to alternating series. Alternating. Can I use this? Yes, I can, because my B is this, which is positive and decreasing. And you do the limit as n approaches infinity of B sub n, which equals 0. And so that means that this converges. So this only works, that little trick. So you identify, so here's the sort of thing that I'm hoping you do for tomorrow's homework, is you're going to look at this and you're going to say, can I do whatever test, try the different tests, and then identify which test you actually end up doing, and then determine whether it converges or diverges. So you've got, this is the test I'm using, here's my work, and the thing converges. So that's the sort of thing we're looking for. All right, let's try this next one, just to see how this shakes out. So this next one, we have the natural log. Oh, what an ugly thing. So we have a natural log of, so that is not a p-series. So let's go through this again. P-series? No. Is it geometric? No. So what are we going to do with this thing? Maybe we can do the limit. So this is that. Here, I'll show you where I am in my flow chart. I'm right there. So I went through these two, geometric p-series. It's neither of them. So let's get down here, because this is a nice one that gets rid of some series that diverge. So notice this only tells you if you diverge. So let's go back and get this. So let's do that. Let's do the limit as n approaches infinity of the natural log of n over 3n plus 1. So what is that limit? Take a minute, see if you can figure it out. Oh, you know what I could do? Just a sec. Let me pull this up. Why is this doing this? There we go. Let me see. Can I plot this? Just a minute. I'm just getting ahead of where we are. X over 3 times x plus 1. Okay. Okay, beautiful. Beautiful. Okay, just wanted to double check something. That, sad. Well, so yeah, I've got an idea for this one, but let's see where we land with this. Just a minute. Interesting. Okay, so did we get this limit? The limit as n approaches infinity? Yeah, I just realized I was thinking the wrong way about this one. Oh, here, I'll find someone. I know you can do this. You can do better than I can because I had it wrong in my head. Michael G. Michael, what do you think of this limit? You certainly could. Very good. I'm going to write this down just for those who aren't as quick as you. Very nice work, though. 3n plus 1, and that's going to equal the natural log of 1/3. What is the natural log of 1/3? I don't know, but your calculator knows. It's around negative 1.1 or something like that. So but it's not 0. That's the key, is that does not equal 0. And because that does not equal 0, it doesn't matter if this is alternating or not. This will diverge. Diverge. So we're using that test for divergence. I was getting scared. I honestly, for whatever reason, I looked at this and I thought, oh, that's going to be 0. So I'm going to have to do like an integral test or something. No, we're done. It's done. Yeah, I don't know why I thought that it was non-zero, or why I thought it was 0. So yeah, I had a graph and everything, and I was like, that graph doesn't. And I realized my mistake. Okay, let's take a look at this next one. So we have this thing. What in the world is cosine of 3n? And also this should be a little n, not a big N. But so cosine of 3n, well, let's explore this just for a minute. So when n equals 1, this is going to be the cosine of 3, wow, over 1 plus 1.2 to the n. Wow, this is, and then you're going to add to this the cosine. Yeah, this is terrible. Cosine of 6, that's not, I guess when I looked at this, I thought it was pi, but that's not pi, that's 3. Okay, that's all right. 1 plus 1.2 to the, we're gonna work this out to the, sorry, this is to the first, this will be to the second. Oh, you want to put it like this? Oh, 3. Sorry, like this. Yeah, this is one problem whenever you have when you lack parentheses or like your argument. I don't know why. Oh, it's almost time to go. Oh, good. So I don't have to do this one. Yeah. So yeah, I was kind of hoping that. Yeah, I thought this was alternating, but it's not. Sometimes positive, sometimes negative. So this is one that we're gonna have to wait. So hopefully most of them you'll be able to do. I think I selected ones that you can actually do. Yeah, that's alternating. So do your best with these, and also look at the practice test. Practice test for tomorrow. I believe it's online already. I'm checking though. So check your practice test, do the quiz,